is driving his car on a dirt road at a constant velocity. So again, going back to this idea of an object moving at a constant velocity. He began his motion 30 meters away from the origin. What does 30 meters represent?
How far? This distance.
Not the distance, but his starting position, right? So that's xi, starting position. He traveled toward the origin, so there's his direction of motion, toward the origin. At a time of 6 seconds, so that's time measurement, he reached the origin, assume there is friction. So he reached the origin is the 0 point, which represents what? If this was his starting position, xf, that's his final position. Okay? So the question is, what is his average velocity? Well, how do we find velocity? How do we find velocity?
0 plus t.
Not t divided by x. Change in x divided by t. The change in the position divided by the time. Okay? Which in other words is the displacement divided by time, which is xf minus xi divided by time. So when we plug in the numbers, okay, xf is 0 meters, xi is 30 meters, okay, and the time is 6 seconds. What do we get when we do the math?
Negative 5.
Negative 5 what? Elements?
Meters
Meters per
per second.
second. So the velocity is negative 5 meters per second. He's moving with a velocity that is constant at a rate of negative 5 meters per second. Everybody understand that? Okay. Now moving back into the tie-in to energy. Gentlemen? Drawing the system schema. Somebody asked, oh, Ms. Bush, what's the system schema? So let's talk a little bit, remind ourselves, review. What's the system schema?
So a little chart.
John.
It's like a thing we like put down things that are affecting stuff, and I see like arrows for each other. So.
Good. So it's a diagram. It's a representation of things that are in contact or things that are affecting each other. And we draw the objects in circles. We draw arrows for the connections between them. And then we also do what to show what the system is. Put a dotted line around the system. So what are the objects that are involved here?
Road, wheel.
Okay, we have the road and the car. Can we just think of the car as one object? Do we have to put a detail with the wheels and the... Okay, not really. We can think of the car as one object. Okay, the person, can we think of the person as part of the car? Yeah, we can. Okay, the origin is just a place. It's a location. It's not an object that's interacting. Okay, so we've got the road and we've got the car. What's keeping the car on the road? The gravitational field, so we should probably include that. Anything else? Okay, it's a pretty simple system schema. The road is affected by the gravitational field, the car is affected by the gravitational field, and there's an interaction between the car and the road as well. Okay? And what's in our system? Everything is in our system. So we show that with our dotted line. What about what? If he's on a dirt road. Okay. Yeah, the person's inside the car, so we can just consider that part of the car. Okay? Alright? So now the next thing that you're asked to do is make the LL diagram for the system. So thinking about the system schema and the things that are involved, thinking about the motion of the object and what's taking place here, what kinds of energy are involved? Let's talk about that first. Is there EK?
No. At 0 seconds.
Is there EK?
Yes.
What is this object doing? Moving, right? So even though at 0 seconds, the time is 0 seconds, we don't know what the object was doing before 0 seconds, and it says that the object is moving at a rate of, we figured out, negative 5 meters per second. So is there EK? Yes, the object is moving with a constant velocity, so there's EK. What about EG?
No.
What is that dependent upon? Where you say the car is. So we could say that our zero EG line is the surface of the road, couldn't we? We get to decide that. So if you decide that the car, okay, here's the car on the road, and that equals zero EG, then that's fine. And you don't have to include EG. If you say that the car is on the road somewhere above what we're calling the zero EG line, then would you have to include EG? Yeah. Right. Okay. If you include EG, what is true of the amount of EG on the left side and the right side? It should stay the same because it didn't tell you that the car is going uphill or downhill. You can assume that it's on the flat surface. Okay. What about elastic energy? Not really. We're not going to include that. What about ECH? Yeah. What is the ECH here? The gasoline in the car. Okay. And technically, if we're talking about the person being part of the car, is there ECH in that person? Yeah. And the ECH in the person is what allows the person to push the gas pedal, right? So technically, there's also ECH within the person, but the person is part of what we said is part of the car. And then what about EDIS? Is there EDIS? Okay. It says there's friction, and we know gasoline, when it makes a car move, there's some heat involved, things like that. So EK, ECH, or EDIS. Now the question is how much of each? How much EK should we put in? Okay, the constant velocity is -5 meters per second. Is that really fast? No. So should we have really lots of EK? No. Okay, remember, the slower the object, the less EK there is. So how much do you want me to include?
Just one.
There's 1 bar? Okay. So 1 bar of EK. Right? How much ECH? 3 bars? Are we going to have a lot at the beginning? Probably. Okay, so 3 bars of ECH. What about EDIS? 1. Probably a small amount again to start with, because the object hasn't been moving very long. Okay. The car is moving. You're told that the car is moving at a constant velocity of, well, we figured out -5 meters per second. It does not say that the car is stopped at 0 seconds. So unless you're told that, you can assume that the description is for that time period. Okay? And then the energy flow diagram, remember, that shows transfers of energy between point A and point B. So how do we make that diagram?
Just write everything.
Just write everything in the box. Why are we writing everything in the box? Because everything is in the system. The system includes everything. So therefore, we can just put everything in the box. If you wanted to, you could list road, car, field. Okay, because those are the 3 objects that are involved. Okay, or you can just write the word everything. Okay, as long as you remember what that represents. Are there any energy transfers into or out of this system? No, because everything is in the system. If there were things outside of the system, then remember you'd have to draw your arrows out or you'd have to draw your arrows in, showing those energy transfers into or out of the system. In this case, that does not exist. Okay, what about a time of 6 seconds? Now the car has traveled at -5 meters per second for a time of 6 seconds. 6 seconds. What is this part of the LL diagram going to look like?
There's no E.
Let's start with the EK. Is there EK? Yeah, how much?
Same about 3.
Same amount. Why is it the same amount?
Oh, it's constant velocity.
Because it's moving at a constant velocity, right? And EK is the amount of energy that is in that motion. So it has the same, so-called level of motion as a constant velocity, so therefore it's going to have the same level of EK. 1 bar. Does everybody understand that? Questions about that? Okay. What about the amount of ECH? Now, it doesn't say that the car has stopped, so there's probably some ECH still left. But what's happening to that ECH? It's going to go down because it's transferred into the EK to keep the car going, right? So how much ECH do you want to include over here? 2? Okay. So we've transferred 2 ECH, or we are left with 2 ECH, which means we've transferred 1 somewhere. Okay, what about EDIS?
2.
Okay, how do we get to 2 here? Okay, yeah, the EDIS goes up as the situation takes place, so we know we need more EDIS here than we had over here, and then we can think about the fact that that one box that was here, that 1 bar of energy that was there, got transferred over, right? It didn't go directly to EDIS. Where did it go first?
EK.
EK, and then EK to EDIS. Okay, so it actually got transferred here, and then from there it got transferred over here. Does that make sense?
Yep.
Okay. So questions about that? Thing to remember when you're talking about objects with constant velocity in terms of the energy is that the EK is always the same. It has to have the same amount of EK because that's what's making it move, right? It's that energy that's stored in its motion. If the motion is constant, the amount of EK has to be constant. So then the question at the bottom, how do energy transfers, goes right back to today's question at the start of the hour. How do energy transfers affect the motion of this object? What do you think? How is energy being transferred in this system?
The gas.
Yeah, the gas in the car, so what's in the gas in the car? E-chemical? What happens to the e-chemical? It gets transferred into EDIS, or not into EDIS, into EK. Which is then transferred into EDIS. Okay, so there's energy transfers constantly taking place to maintain that constant velocity. The energy from the chemicals in the gas are transferred into the motion of the car, which is then transferred into heat and sound and light and things like that as heat is. Questions about that?